GCSE radioactivity. So first off, we need to do a little bit of basic chemistry revision. So first off, we're going to quickly draw and label an atom, see if you can do it. So just the basic structure. On your outside, you have your electrons. What have we got in our inside? Our nucleus. What's in our nucleus? Our nucleons, which are our protons and our neutrons. So we need to know some of the other basic terms as well linked to these atoms. Ions, isotopes, and we need to make sure we're aware of our mass number and atomic number. So let's do a little basic reminder of these subatomic particles. We've got to know their mass and their charge, or their mass and their relative charge. Electrons, protons, and neutrons. So mass of electrons, their relative mass is effectively 0 compared to the others, or about 1 over 1800. Their charge is a -1. Protons, relative mass is 1, charge of +1. Neutrons, mass 1, charge of 0. So let's quickly then link that to our mass number and our atomic number. So if we think of let's make up a random element X, and then we've got, let's say that there was a number 7 here. So this isn't real. There'd be a different element if it was 7. And let's say that the number up here was 15. So the atomic number is the smaller number, and the atomic number tells us how many protons are there and how many electrons are there in an atom, because atoms have the same number of electrons and protons. So if you look at this one I've drawn over here, so I've actually drawn too many protons because I've got 2 orange ones there, and if these orange things are the protons, and these are the neutrons. I've got to have 2 protons there because I've got 2 electrons on the rings on the shells on the outside. So for this one, if I've got an atomic number of 7, that means I've got 7 protons, and I've got 7 electrons. Well, let's think about that. That means we've got a +7 charge and a -7 charge. So of the atom as a whole, its overall charge is 0. Our mass number up here. So our mass number here, and that's the mass of the nucleons. So remember, all the mass inside the nucleons of the atom. There's not much mass at all on the outside in the electrons. So we've got 15 there. Well, we've already said there's 7 protons. So we do 15 minus 7 gives us 8. So there's 8 neutrons there, because this mass number is the number of protons plus the number of the neutrons. Okay. Now, why have we ignored our electrons? Because we've just said that their electron mass is very, very small compared to the protons and neutrons. So we're not taking that into account into this mass number here. So if we look at the atom I drew over here, and we look at this nucleus, so I've got 3 neutrons and 2 protons, so its mass number would be 5. Nice and basic stuff that we would have done in our early lessons in chemistry. So let's remind ourselves of some of the other keywords we need to know. What do we mean then by an isotope? So an isotope is an element that has it's the same element, so it's got the same number of protons. So here I still have the element X, okay, because it's the number of the protons, the atomic number, which dictates what the element is. If you have a different number of protons, it has to be a different element, okay? But let's say I had 16 now as the mass number. That means that this element, this isotope of this element X, has an extra neutron in it, okay? So this one's got 9 neutrons rather than what we said before of 8. And that's why in your chemistry you would have done why some elements in the periodic table may have, for example, chlorine is the famous example of 35.5, because some percentage of chlorine atoms have got a mass of 35 and some percentage of chlorine has got a mass of 37. So you can work out it's the weighted average of that. Now we don't need to go into that here, we just need to be aware of these basic terms for our physics and radioactivity. So isotopes are just elements, same elements have a different number of neutrons in the nucleus. Now what about ions? So ions are when we have our atoms again, which we just said over here with the atomic number, they have the same number of protons as they do electrons. So overall, their overall charge is 0. Okay, well, if we've got our nucleus here that's got 2 protons in it, so let's say there's a P there and a P there, and we've got 2 electrons on the outside, so its overall charge is 0. But what can happen is these electrons can be moved like you've done in chemistry. That could be due to chemical ionic bonding, covalent bonding, where they share them. So these electrons can be moved or knocked off by different mechanisms. So if an atom was to lose an electron, Well, that means it's now got one more proton than it has got an electron here. So this would have an overall charge of +1. Okay. In the same way, if something gained an electron, it would be a charge of -1. So ions, they have the same, it's the same element, but it's gained or lost. There's a gain or loss of electrons. So how does this link to radioactivity? Why are we talking about these ions that you do in chemistry? It's all to do with this term, ionizing radiation. This topic is not just about, we use the term radiation for lots of things. You could call that normal light, normal visible light of your electromagnetic spectrum is radiation. That's light radiation. Ionizing radiation is different. It's harmful. It's ionizing. So this word ionize, in the hint in the name there, it turns atoms into ions. So when ionizing radiation comes along, it can knock these electrons off. It can knock these electrons off the atoms, okay, and turn them into ions. Now, when that happens in your DNA over here, when that happens in your DNA, when we have ionizing radiation come on and it ionizes atoms in your DNA, that's very bad, okay? That can lead to the DNA repaired incorrectly, which can lead to cancerous cells. So when the DNA replicates, it could repair incorrectly and cause cancerous cells, which obviously could replicate and grow and spread and cause a tumor. It may repair correctly and be fine, and you're okay if you haven't got too much ionizing radiation. Or what can also happen is the DNA is literally destroyed and the cell's been destroyed, and that's kind of what happens when you have so much ultraviolet light on your skin and you get sunburn. The cells have been destroyed. So that's why it's called ionizing radiation. Let's go a little bit into the history of ionizing radiation. Now, this bit about Marie Curie and Henry Becquerel is not explicitly on the GCSE specifications for exam boards. However, it's good to know about them and their names because it often gets brought up in questions. So Henry Becquerel is the person who kind of discovered ionizing radiation. So the story is that he found he had some iron ore in his desk, in his top of his drawer of his desk here, and he had some photographic film in the bottom drawer. So if you imagine that old photographic film that changes colour when it's exposed to light, and then he had it in a brown envelope so that there wouldn't be any light in there. And above, in the middle drawer, he had a key, and he'd left this in there for a couple of weeks. And he went to use his photographic film, and he realised, oh, he's got an image of a key on there. So he kind of realised that although he couldn't see it, there was something shooting off that uranium ore that he had, that rock that he had in his top shelf there, some of these uranium salts, and it affected his film that hadn't been exposed to any light. So he kind of realised that there was something coming off there. And then it was Marie Curie who famously went on and did a lot more work with this radioactivity stuff and came up with some of the first uses of X-rays during the First World War, and then she famously passed away. Her and her partner Pierre Curie, she passed away from the leukemia that was caused from her exposure to radioactivity. You can actually go see Marie Curie's lab notes, but when you go and see them, you have to wear radioactive protective clothing because her notes are so radioactive still. So what do we mean by this word radioactive? What's the term actually to do with? So that means that there is an unstable nucleus. The nucleus is unstable. What do we mean by unstable? It's got too much energy. Too much energy. Okay? And to kind of release that energy, to become more stable, it may give off radiation. So that may be in the form of alpha, beta, or gamma, or it could give off a neutron as well. So it could be neutron radiation as well. There are things like X-rays and stuff as well, which I'm not going to go into because that's not on your GCSE. When the nucleus gives out this radiation, it becomes more stable, and that's called radioactive decay. The nucleus has undergone radioactive decay. So we've got to be careful. It's not coming from the atom, it's coming from the nucleus itself. Now, we say that this process is random. Now, you could be thinking, oh, wait there, well, we know uranium's radioactive. How can you say that's random then? Because although we know it's radioactive, we cannot predict exactly which nucleus and when it will undergo radioactive decay. So if you imagine that you've got billions of nuclei of atoms in a material, we can't predict exactly when each one will undergo radioactive decay. We can just predict an average of what will happen. So the key word there was unstable and random. I would be aware of this part of the course. It's come up before in very weird questions. I recall an exam question from a few years ago where the examiners must have been trying to think of a sneaky way to question about this without making it too obvious. And they were questioning about, if you put popcorn kernels in a microwave, how is this similar to radioactivity and radioactive decay? And you had to talk about how that you couldn't predict exactly which kernel was going to undergo radioactive decay, and when the kernel popped, it was like a nucleus undergoing radioactive decay. So quite a weird question. So be aware of these basics. Some safety things now with handling radioactive sources. So this is under kind of like a core practical experiment. Now, it's not an experiment that you would be allowed to do yourself. You're only allowed to handle radioactive sources when you are in sixth form. It's one that your teacher may show you. If you're lucky, your school will have radioactive sources, and the teacher will be able to physically show you this, or they may rely on a video demonstration to show you. So some things before we go into this, there's some key words here. There's contamination and irradiation. So we've got to be really careful that we distinguish between these two words. When something has undergone irradiation, that means that the radioactive source itself. So if we've got a radioactive source here, that means it is giving out some radiation that we can't see, and that you are standing over here, and you have been irradiated. Okay, so that radiation has hit you. Okay, done some damage to you. Okay, it's gone into your cells, and then it's passed through you. Okay, or it's been absorbed into your skin. So if you've been irradiated, it depends on how much of that dosage then you've been irradiated from. Okay, how much damage it would do. But that radiation could be absorbed or passed straight through you. It's not. That means that you haven't physically touched the radioactive source. You haven't actually touched it. You've just been exposed to the rays or the particles that have been given off. Contamination is when you've actually got some of this radioactive material on you. So maybe you've scraped against it and you've got it on your hands a little bit, or maybe then you've touched your mouth, or maybe that there's some radioactivity coming off because there's a fire and there's some radioactive material on fire and it's gone into the smoke, and maybe then you breathed it in. So that could obviously be quite serious, because now that radioactive source is inside your lungs and is going to continue to give out and irradiate you from the inside. So contamination can be quite serious. Irradiation could be quite serious as well, depending on the dose that you're given. So we have to be careful that we distinguish between these two words, contamination and irradiation. This often catches people out on exam questions when you have questions such as, for example, maybe it's my awful drawing of an apple, that maybe you've got some apples that have, and the question will tell you that the apples have been irradiated. Okay, so it's gone through a machine and they've been irradiated deliberately. Now that kills the bacteria on the apples to help them last for longer. So that's a good thing. And it'll ask you, why are they safe to eat? And people think, oh no, it's been irradiated, that's bad, it's not safe to eat. Well, no, it's fine, because the radiation has passed through. When would it be unsafe? Would be if some of this radioactive material got on and stuck onto the food, and then you eat it, then you'd be contaminated. So we have to be really careful about these two terms, irradiation and contamination. So what is this experiment? What some safety precautions first? So to prevent irradiation, that's with an A there, sorry, I spelled that incorrect. To prevent irradiation, your teacher will, when they hand these radioactive sources, they're going to use a couple of safety things. So the number one main thing to help limit exposure is to point the source away from themselves. So when they get out the radioactive source from these lead-lined things here, they've got lead to protect us so the radiation can't escape outwards. Okay. Radiation can't escape from those things. So lead line, well, it can actually leak out a little bit. The gamma radiation we'll talk about in a second would actually leak out a little bit. But they're gonna make sure that that is shooting away from them. So they're gonna put it in a track here, and they're gonna shoot it that way. And the person showing the demonstration is gonna stand over here. Okay, so they're not being exposed, so they're always gonna point it away from them. That's one thing they can do. The other thing they could do is just literally, so they're gonna direct it away. Another thing they can do is literally limit the time of exposure. They're going to make sure they're not exposed for it to a too long period of time. Another thing they're going to do, especially say there was an accident and they dropped it, or how would they stop the students being exposed to it if they accidentally pointed it at the students for a second or two, is that the students and the teacher would step away. So every time we have a larger distance, the distance between you and the radioactive source is going to decrease the amount of dose that you get exposed to. And that's also linked to the tongs as well. You also use tongs, and again, you're having a longer distance from you to the radioactive source. What about things to prevent contamination? So this is actually quite a bad picture here, because the person who's getting out the radioactive source is not wearing gloves. So you should still wear gloves, even if you are using tongs, because technically, could there possibly be a small amount of radioactive debris that's been let on these tongs, and then he's touching the tongs and it's going to be on his hands. So you should still wear gloves to prevent contamination. Another thing that, if not so much in this experiment, but if it was in a accident in a like in Fukushima or Chernobyl, and there was smoke in the air, one thing you would wear to prevent contamination is a mask to stop those debris going into your lungs. Another thing you can do if you are demonstrating radioactivity like here, you may put some newspaper down onto the surface, onto the table here, okay, and that's going to prevent that if the teacher does put the radioactive material on the wooden desk, it stops any radioactive debris being left on the table, which could stay there for many years. So it then go on the newspaper, and the newspaper could be put away and chucked in the bin. So those are some things to prevent contamination and irradiation. Other things that we need to talk about is, what does the experiment actually involve now? So you've got our Geiger Muller tube here, or Geiger counter. So that's the thing that clicks in movies and stuff and sounds quite scary when you put a radioactive source next to it. So that's our detector. That's our detector over here. It's going to detect the intensity of radiation. Okay. So the first thing that to detect where the radiation is going through first, the first thing they need to do is they need to detect background radiation count. Okay, because we are surrounded by background radiation all the time, so they need to check that level and they need to see how much radioactivity is just in the room in general. So they do that without having the radioactive source there. They're just checking, so that this source is not there, they're just checking the background count. Once they've done that, then they'll write it down, and then you've got a background reading. Okay, and now we can start testing the radioactive materials. So you're going to put it in, and you're going to use a ruler. You'd have a ruler along here to keep your distance the same, and you're going to choose a distance, and you're going to investigate the sources. So you may pick an alpha source or a beta source, which we'll talk about in a second, and you're going to check to see, first of all, you could investigate distance. So you're not going to use anything to block it, and you could change this distance from the Geiger counter to the radioactive source to see how much air can the radioactive sources penetrate through. And then you could investigate, let's check now what can absorb this material. So what type of materials could absorb the radioactive the radiation trying to pass through. And the general things you'd use is paper, aluminium, and lead, and investigate which ones can get through paper and which ones can get through lead. And you're going to check the count rate then. Does the detector change massively in count? Okay, so we're going to check that count rate, and we're going to use absorbers of different materials: paper, aluminium, Al, and lead, Pb. So we're going to check which things can penetrate through. And we would also have investigated the distance in air. So what do you find out when you do this experiment? After you've carefully put the source back in the lead line box, the teacher put it back in the box, what would they have found out? You would have found out that alpha particles can get blocked by paper, or even just by a few centimeters of air. So alpha will not penetrate paper or even skin as well, and a few centimeters of air. Okay, whereas beta would go pretty much straight through the paper, but would get blocked by a bit of aluminium, a few millimeters of aluminium. Gamma would go straight through paper, would straight go through a few centimeters of aluminium, no problem. It would take a few centimeters of lead to pass through, and it would pass through several meters of air. Okay. What you also could have checked is the intensity of the radiation. The intensity, how much ionization is it doing? So in this here, you would have found out that alpha, although it was very weakly, so let's do a little summary for alpha. Alpha is very weak in terms of penetration. Okay, barely got through that skin or that paper. However, you would have found that it is very ionizing. So you can't just say, oh well, alpha is not dangerous because it couldn't get through my skin anyway. But it would, if it got inside your body, be very, very harmful. It's very ionizing. It's like we said there about irradiation and contamination. An alpha radioactive source or radioactive isotope is not very dangerous in terms of radiation, but it is extremely dangerous in terms of contamination if you got it inside your body somehow. So we use this symbol for alpha. We use an A like that, and we use a 4 and a 2. So now you guys should be able to know what that 4 and that 2 meant. From what we said earlier, this means it's got 2 protons and 2 neutrons, because that's our atomic number or mass number. So what actually is an alpha particle It is a helium nucleus. Just the nucleus. So that means it hasn't got those 2 electrons. Well, what does that mean the charge is? Well, that means it's got an overall charge of +2 because it's got 2 protons, but it hasn't got the electrons on the outside. So and that actually explains why it's so ionizing, because it's got a strong +2 charge, and it's also quite a heavy mass. If we think back to that word at the start, what did we mean by ionizing? Ionizing was when we were knocking electrons off the atoms. We're knocking these electrons off the atoms to ionize them. So if something like an alpha particle is very heavy and it's got a mass number of 4 and it's got a charge of +2, it's going to be better at knocking off those electrons. So alpha is very dangerous if it gets inside your body somehow. +2 charge and heavy mass. What about the next one? Beta radiation. Oh, sorry, one more thing about alpha. Because it is a helium nucleus, we sometimes write it as He with the 4 and the 2 rather than the alpha symbol. What about beta? Beta was in the middle, wasn't it? It went through paper, but it got blocked by a few centimeters of aluminium. And you would have found that that is a medium of penetration, and it's got a medium ionizing power. It's quite harmful. You're getting irradiated with beta, that's not good. There could be a lot of radiation. So what symbol do we use from beta? We use a 0 and a -1. So what's got a relative mass of 0 but a charge of -1? It's an electron. So all we mean by a beta particle is a high-speed electron. All it is a high-speed electron. Okay, it's got some charge, because it's obviously got a charge of -1 charge. That's why it's a little bit ionizing. And although it's got a relative mass of 0, like we said earlier, it's actually 1 over 1800, isn't it? Compared to a proton or neutron. So it has got a little bit of mass. Okay, it is a particle. Okay, in the same way like that helium nucleus is an actual particle. Now what we need to talk about beta, which we will do shortly, is where's the beta particle? Where's this electron actually coming from? Because it's not coming from the electron shells on the outside. We'll talk more about that in a bit because we don't want to confuse things. Last one is the easiest one to remember generally, is gamma. So gamma went straight through the paper, would go straight through the aluminium and takes a few centimeters of lead to block. So it's highly penetrative, but it's weakly ionizing. So if you got irradiated with a little bit of gamma, it's not the end of the world, but if you got exposed to it for a long period of time, then it could be harmful. But it's weakly ionizing and it's highly penetrative. Why is it weakly ionizing? Gamma, you should recall, is an EM wave, an electromagnetic wave from your electromagnetic spectrum. So remember, radio, micro-infrared, visible light, ultraviolet, X-rays, gamma wave is an electromagnetic wave. It's not a particle. Okay, now what does that mean? We use this symbol for gamma. It looks like a curly Y, and it's a 0, 0. So it's got no mass and no charge. Because it's an electromagnetic wave, no mass and no charge. It's just a high energy, high frequency wave. Okay, so it's kind of like X-rays and ultraviolet, they're high frequency on that electromagnetic spectrum. If you remember, goes something like that, and you have radio, micro, infrared, visible, ultraviolet, X-ray, gamma ray. Gamma rays are high frequency ones, high energy, and that's why they are ionizing, but radio waves, which are lower frequency, are not. So let's go into a bit of the nuclear equations now. Before we do that though, we're going to come back to beta, and we're going to say a little something else, because we said that this was a high-speed electron, but we said it's not coming from the outside on the electrons. So what actually happens in beta decay is inside the nucleus, something must be happening to give out that electron. So what happens is inside the nucleus, you have protons and neutrons, don't you? So to give out an electron, what happens is a neutron changes into a proton. So a neutron in the nucleus changes into a proton. There are reasons why it does that, but you do that if you do A-level physics. Now the proton stays in the nucleus. That stays. whereas the electron or the beta particle goes shooting off. So the electron is emitted as a beta particle from inside the nucleus, so that comes shooting off. So we've got our nucleus there, and we've got a neutron, and that's changing into a proton, and our electron is coming shooting off as a beta particle, and that's the thing that's doing the harm. Let's then look at, we need to now link this to what's going on with nuclear equations, which some people find very, very difficult. Though once you get them, they're easy, and they're actually very easy marks. So, and to do that, we have to know and remember what we said earlier about the atomic numbers and mass numbers. So let's do alpha first, because alpha was a little bit more straightforward. Now, in physics, you are not given a periodic table. So you're never expected to know the elements off the top of your head. So I'm going to use an X, and I'm going to say it's going to decay to an element Y, and it's given off an alpha. But you could be expected to fill in the blanks, okay? So if they told you that X had, I don't know, let's say it was, let's say it's 97, and it's got a mass of 158, you've got to then fill in the blanks for Y and the alpha. So we know alpha was a helium nucleus with 2 protons, 2 neutrons, so that was a 4 and a 2. Now, whatever's on the left side of the arrow, what happens before, must be the same afterwards. So the atomic number and mass numbers overall can't change. They must remain balanced, okay? So if we got started with 158 here, we've got 4 here, so this must be 154 for it to be equal. If we've got 97 on the left, we've got two protons go into the alpha particle, this must be 95 here. Okay, nice and straightforward, this nuclear equation for alpha. Okay, just remember they've got to be balanced on either side. Now you guys try this one. So we've got PO, polonium, go into He, so remember that He is another way of saying alpha because it's a helium nucleus. What would the atomic number be for lead? Okay, so stop the video and have a go of that one. Let's quickly go through it then. So always fill in the radioactive part first, because that's the easiest bit for you to do and to remember. That's a 4 and a 2. And now we can work out, right, we've got 84 on the left. What must be on the right? We've got 2 going there, so this must be 82 there. What must the mass number be on the left? Well, we've got 4 going to He, and we've got 204 on PB, so this must be 208. Now, if you're checking through your periodic table, and you're thinking, oh, well, PB hasn't got, I'm not sure what it's got off the top of my head, the mass number, or PO hasn't got the mass number of 208 in your periodic table. Remember, don't worry, because these could be isotopes. They may have different mass numbers. So if you know all your mass numbers from chemistry, don't panic and confuse if they're different. Next one, let's now look at beta decay. So let's think about what we said is actually happening. A neutron in the nucleus is changing into a proton, which stays in the nucleus. It's giving off an electron that goes shooting off, okay? So in beta decay, again, let's now say that you start with some element A, and it goes to some element B. Let's not use B, actually, because we're going to use beta. Let's say it goes to some element Z, and it gives off some beta particle. Same thing as before. What would happen to these numbers here? Okay, so let's say that this number for A was 19, and this number is 29. What is going to happen to the numbers for Z? So for beta, first thing we do is fill in its mass number, which was 0, and its atomic number there was -1. So a neutron and a proton have the same mass, and that's why this mass number here is 0. So what does that mean it's going to be here? It's got to be the same, isn't it? It's still 29. The relative masses are the same. Neutrons and protons are the same. But now let's think what's going to happen with Z. Why is it changed element? Well, it's changed element because it's changed protons. It's gained a proton, hasn't it? So a neutron has changed into a proton, and that's stayed in the nucleus. So that's why the atomic number has gone up to 20. And we can check that then. We say it's got to be balanced on either side of the arrow. So we've got 19 there, we've got 20 here, -1, so overall that's still 19. It's still the same as that atomic number over there. Let's now, you guys, quickly try this one. We've got iodine going to xenon plus E. Stop the video and have a quick go. Okay, let's fill this in then. So we've got our mass number of 0, we've got our -1 there. Let's do that one first for our beta particle. So we now know, right, 0 mass, so mass number is the same, so straight away I know that's 131 there. Now I know that in my nucleus, my neutron changed into my proton, so that's gone to 54. Yep, check it. 54 minus 1 is 53. It's the same. Nice and easy. 2 or 3 marks in the exam. Easy level 9. Last one is the easiest one for these nuclear equations, and that was the gamma. Why is gamma easy? Well, what did we say its numbers were? Its mass and atomic number. It's just an electromagnetic wave. It's got 0, 0. Okay, so we barely even need to do this one. If we start with some element A, what's it going to end up as? Let's say it was 18 and 26, make it up. It's going to go to alpha, we know that's 0, 0. So what is it going to go to? It's going to be the same. It hasn't lost or gained anything, it's the exact same thing. All we're doing there by giving off this alpha, this gamma ray, is releasing some of that energy from the nucleus, which makes it more stable. So these nuclear equations should be nice and easy. Now, like I said earlier, don't just focus on them though. Focus on the basics that we've talked about earlier, and some of these little extra things to do with radioactive safety. And the number one thing that people forget from everything we've talked about is remembering to take that background radiation count when you do this experiment. Okay, that's how you check how much radioactivity, how much intensity is coming off the actual radioactive source or the radioactive isotope. The next video I'll carry on with this topic to cover half-life and background radiation. Thank you.